right, Mr. Köllner has been with Vector for 3 years, and he studied computer science at the Karlsruhe Institute of Technologies. So he's also an engineer, so he's got the best of all worlds. And he's the head of a small development team at our site in Karlsruhe, and this is exactly what he looks into: service-oriented architectures, new paradigms, and how we are going to work with them. And he's going to enlighten you on that. Yeah, thanks very much. Welcome, service-oriented architectures. Well, is this an old story? Isn't that being done by software people for 20 years? And Canoe can already do some IP. We've already built that in. So why am I here in front of you telling you something? Well, in fact, actually, we went back and thought about it once again. Service-oriented architectures, or SOA, are a trend which will have a major impact. And we found that in our infrastructure, in our Canoe infrastructure, we have got to improve the system. We've got to improve our interfaces so that we can support these scenarios effectively. And the solution that we've come up with is the so-called Canoe Function Bus. This is what I'm going to tell you about in my presentation. So I'm going to make a prophecy, and that is that the EE architecture in the vehicle is undergoing an intensive transformation. And of course, EE architectures is something that have contributed to economic development. There are certain trends. There's connectivity, which is going to be built into the vehicle, which means that the vehicle will connect with some things like CarPlay, cloud services. It will download updates, and there are new business models that are emerging based on that. Then, of course, there's a trend of electrification, and there is a positive trend to be identified, and that is that the manufacturers will plan to completely redesign their EE architectures. They might say, well, some ECUs have become obsolete, so why don't we redesign such an architecture completely from scratch? Then autonomous driving. The architecture that will help autonomous driving or automated driving. Well, we don't know exactly what it is going to look like, but we know that we will have to process much more data. We are talking about fail operational redundancies that we have to build into the vehicle. And in fact, given these technology drivers, there is an essence, there is a conclusion that we drew, and that is that the service-oriented architecture will replace embedded systems. So you can always come up with a signal flow diagram. You push a button, and then a C code implementation will be the result with an init and the main function. And the main function is retrieved periodically. So that fits in very well with the static scheme of such a real-time system. But try to trigger or model an update process with a cloud server, for example, or try a new function in a vehicle, for example, in the connectivity environment. So you will get to some limits, and well, how can we approach this with methods of software engineering, encapsulation, polymorphy, maybe coming back to good old code? How can we engineer such code? And if I take my develop class and put it into an interface, publish it versus other software components, then what I come up with are services. And all that is service-oriented architecture. So let's take a look at the SOA architecture. The classic is AutoSAR, a wonderful component-based design, ready for SOA because of the client-server interfaces. But except for variants, it is a rather static topology. And this is a deficiency that people recognized. And AutoSAR, the adaptive platform of AutoSAR is being developed currently. And we're going to hear a presentation, a first-hand presentation on AutoSAR Adaptive tomorrow. And I'm really looking forward to find out more about the dynamic features and what it will look like. Of course, we're also listening to the community, especially on the Internet and Things. There are new standards being discussed, new standards being established. So this doesn't mean that we would already have incorporated them in our tool. We're just following the discussion there, and we are trying to find out what's important. We're going to follow the wishes of our customers. But of course, it's going into a similar direction. That's why we think it's so interesting. Let me come back to the special requirements of SOA middleware. Now, SOA, service-oriented architecture, we're talking about asynchronous remote procedure calls. If the client makes such a call, then it doesn't matter whether the method is implemented remote or next to the call. So the arguments are just being serialized via a network. On the other side, there's another middleware. It will unpack the arguments, will do the actual call, and then it goes the other way around. Now, certainly, we have prolonged processing latencies. A remote call lasts longer or takes longer than a local call. And that's why what we're using are asynchronous patterns. So this is how the client has the opportunity to use the time before the call comes back to do other processing tasks. Now, if we talk about SOA and AutoSAR, then there's only one choice, and that is some IP. Some IP used to be specified by INB, and it is now integrated into the AutoSAR standard. And there's an interesting case study here, because services are described by interfaces in some IP. It's a bundle of methods, and there are events as well. And these are reverse remote procedure calls or procedure calls, and then there are fields. They are a meta construct from a getter and a setter method, or getter-setter methods. So the client can call some data actively, or the server sends it. And events are just not sent just like that, but you've got to subscribe to them. So they are put together. It's an event group that will save you some network bandwidth to do that. And what's also remarkable is in some IP, there is a service discovery. Well, for SOA, you need it anyway, but the current status is we're talking about static topologies. And that's why I think it's remarkable that service discovery was designed into this here. Because if my ECUs are static, then I can assign a static IP address and a static IP to them, which means that my middleware would know by itself where a service is to be localized. So why do we do service discovery after all? And I can give you the answer, and that is it lies in the startup times of ECUs. So the reason is that services could build upon each other. One ECU depends on the services of another ECU. And if this is the case, then we don't want any static timeouts to be designed into the system so that they have to wait for service to be available. We need a service discovery where the service says, well, hey, hi, I'm the service and I'm ready to go. And the ECU can continue processing. And I would like to come back to another also very important use case, a use case which we've always been taking care of, and that is virtual integration. We know that from function to an ECU, it's a long way. You have lots of iterations via different departments, via different suppliers. And the users, that is our manufacturers, but also the suppliers, are to be supported in a very early stage of the development and design. So already in the simulation phase, we would like to be able to integrate it. So we distinguish simulation nodes and virtual ECUs. So we're talking about a piece of abstract code, and a virtual ECU, on the other hand, is a virtual prototype. So true AUTOSAR code is in it, and it was integrated against a runtime environment. So we've taken this one step further, and here we want to make sure that if in later stages more virtual prototypes are available, we want to be able to switch to them during simulation, and at some point the real ECUs are on the table, and then we want to be able to support both the real and the virtual ECUs. And if we take all this together, the communication paradigms of AUTOSAR, SAM-IP, and the adaptive dynamics, we came up with a solution, and that is the Canoe Function Bus. In order to explain it in more detail, we can take a microscope. We thought up some micro particles, and we call them communication objects. They're like little molecules. So they are individual participants. You could also call them ECUs, because you as a user can group the functions as you like. What's important is that the communication object guarantees communication among these participants. So the communication objects can be signals, a PDU, a remote procedure call, and services, and they are based on some IP, or they are like some IP. Every endpoint represents a logical participant. Logical means that they could be real physical devices, or it could be a shared IP address or the same MAC address. So the logical participants are grouped just according to the wishes of the user. Now this is a communication object in more detail. It could be a camera interface. This camera interface means that in a car we could have different cameras. Every service instance is represented by such a server endpoint on the ECU. And as a service user on the client side, we've got the ECUs which use this camera or want to use this camera. So the question is, where does this object come from? As a user, you can define this interface, you can configure it as you like, but we are going to do our best to make sure that in Canoe we have an AUTOSAR communication description, or from AUTOSAR virtual target we can derive a corresponding configuration, and you will be in a position to configure these endpoints depending on the design of your setup. And we can also look at this on the basis of a specific example. This is a CU with two endpoints. In the upper layer, it's got an access API where applications can access the layer, and then there are protocol layers below that. This is a communication object of the type service, and these protocol layers have been connected, and we're calling this a binding block, which means that at some point we might replace this by a different protocol. Now you can play around with this setup. On the one hand, you could configure it such that one side is a real physical ECU and the other one is just a simulated ECU. So you would have to configure these protocol layers just to make sure that Canoe knows where to address the calls. But then we can also configure it such that both sides are real. So then this would be communication outside Canoe. But if as a user, I might want to be able to measure the communication between two ECUs, then we would provide a measurement port so that this communication, if you have described your model in Canoe, you can measure the communication and supervise or monitor it. A third very important use case, we're in a purely simulated world. two simulation nodes or simulation node and ECU. That's really up to you. Then these protocol layers will just be switched off, and we are going to realize an abstract transmission on this CO. This will save you simulation bandwidth, and it has this at the same time the advantage that there's no necessity to configure these layers. Because very often you're confronted with a case where a communication matrix isn't even available or it's not stable yet. So it would be annoying if the integration at the function level fails because some parameters in the function description are inconsistent. So we're trying to be more realistic by making sure that we're offering transmission models, so you can use or apply a certain latency or also simulate cyclical transmission behavior. Now let me move on to some of the testing concepts. Let's talk about the classic domain, a case that we're seeing quite frequently still today. In Canoe, you can write a CAPL program based on the CAN message base. Your test can be configured. So Canoe has always been able to do that. And our advice for the users is that they should not do it this way, because Canoe has an interaction layer and by itself is able to package these messages and unpack these messages, and the best abstraction level is the signal level for this purpose, against which you can then code your tests. And then there's another case based on virtual target where we can integrate at port level, and there you can also write a test against system variables. And it's quite a good approach also generically, because you can keep in your head that system variables can be mapped against other variables or signals. So you can gain some level of abstraction, and the Canoe system variables today are a precursor of the function bus as we have it available now, or as we are presenting it today. But they will remain in Canoe. They will remain available in Canoe. If we take a look at the service-oriented domain, then our idea is to make sure that the test can be coded against the function bus at the most abstract level possible, with the side effect, the favorable side effect, that it doesn't matter to the test whether the SUT is available in the real or the virtual world. We just reconfigure the bus and the participant, and the function bus will just route this on for you. Just an overview of the interfaces that we have come up with. On the one hand, we have extensions in the field of service discovery. We also support some IP here, but what we've also thought about is that we are trying to become more abstract. We are offering what we might call an abstract service discovery. Today we only have some IP, but other protocols could be interesting because we want to offer the user as much usability as possible. So we have features to make sure that the service discovery can be switched to an automatic mode if this is not if it is not important for my test how this service discovery actually works. We also have mock-up of services, service mock-up, and the service that we have come up here is the answering machine, as we call it. So if there are calls with a pre-configured, they are answered with a pre-configured default. And I haven't even talked about dynamic endpoints. We have the possibility now that as user, if you have as COs and runtime, you can create dynamic endpoints, which means that you can instance the services at runtime. Wait functions also were required, new wait functions that you can use in a test mail, and then symmetrically to that, we have the handlers that are available in C# and CAPL. So when a service is discovered, a method is called or whatever. I mean, I think I could also show it to you by means of a code example. So I have one in C# and one in CAPL. And in fact, we needed a special syntax to be able to address the endpoints of a CO. So you can see the front left cam and the head unit, which is referenced here. And we found the means to make sure that we can do justice to both languages. I mean, it's a bit of C# and also CAPL philosophy, but you know, we've introduced a new concept. These are the waiting handlers. They kick in when you have a service, when you implement a service in the sense of a routine which does the processing. So it might be that this service already needs simulated computing times, or that it depends on other services because that would also use time. And we have a little special tag to make sure that the handler is allowed to use simulation time. And this brings me on to my summary and conclusion. So SOA is a trend which really spreads in the automotive industry. We also believe it's a sustainable trend. It's an important trend. This is why we came up with the function bus. The function bus is a simulation backbone which supports the relevant communication paradigms. Then use cases such as virtual integration and also the integration of virtual and real integration. And of course, the function bus is not limited to SOA. It also subsumes the signal-based domain. And you also have advantages if you use it for that purpose simply because of the use cases that are just simplified. And then the question becomes, well, when will it be available? We have to say that it is a major project and we would like to release it with Canoe 10.0 simultaneously with the vRvirtual target because the function bus offers some added value if we have an abstract integration of software components. But it's actually quite a major project which will just span several service packs. So we're already developing it, but these developments will be ongoing because there are impacts on all different features of the software. So thanks very much. That would be it. And I look forward to your questions. Oh, thank you, Christian. I think I have finally come to understand what we are actually doing. But maybe there are questions from the audience. So Ethernet, some IP, these two catchwords, is all this limited to Ethernet? Well, the function bus as such is abstract. So initially, it's that we want to support these abstract communication particles. But of course, we cannot just remain in the abstract environment. That's why we said it makes sense to add some IP with Ethernet. But of course, we're open to other technologies and other protocols. Thank you. Jürgen Dorit from MTU in Friedrichshafen. Yes, function bus on CAN. How does that work? Could you give me an example? Now, the abstraction that you would take from the function bus would be the classic signal, your classic signal. So that would be a successor to the system variable against which you would usually code And the advantage would be that you do not have that it doesn't make a difference whether you configure against a system variable or Canoe. So today it's a difference. You have a @ or a $ character. So we want to harmonize that. And furthermore, a protocol layer would be below that. For CAN, it is a bit simpler. But otherwise, your test would be built just the same, but you would then be able to use it both for the abstract and for the real world. Thank you very much. Maybe you could give us an example. Once Canoe 10 is out, how it can be done. You said, well, it's $, that's the dot, or an @ character. So it would be great to have a more specific example to see how that works. Janan Koser from Daimler AG. Are there any considerations to have a generation wizard for the functional bus? Because if you had such a generator, you could generate a system description and to do a residual bus simulation with a functional bus, but without detailed network information. Are there any considerations in that field? Yes, actually, we're planning this explicitly. Communication descriptions from AUTOSAR are supposed to be imported to be able to derive COs, including their protocols, and to be able to configure them. And if you then connect this with our features automatic answering machine, then you have a similar thing as a residual bus simulation transferred to SOA. So calls can be answered without you as a user having to have to build them. So actually we have been able to derive relevant bus traffic. Of course, you need an AUTOSAR description which is complete. So the tool will have to cover both. Some tools have a complete AUTOSAR description. Others you will have to do some manual work in addition to that, and you will then come up with the same result. All right, I think that concludes this. Thanks very much. Thank you.